Hello everyone, welcome to Lab 2. Today, we're gonna go over some transformers. Transformers are so important to civilization as we know it. And it starts with this problem. Let's say you have a generation plant, power generation plant, and it is gonna be, okay, but it starts, oh my God. Okay, and it starts with this. Let's say you have a generation power plant. It's usually going to be placed really far away from civilization because I don't think anybody would want a megawatt or gigawatt power plant right next to their house. That sounds like a disaster waiting to happen. So usually they're placed really far away from a city, from where the actual customers are. But that creates a problem of distance. How are you going to get that power all the way from there to you, the customer, right there, over there? Okay, you want your 120 volts to power your house, but you're really far away from where the power is actually coming from. So you might answer, okay, transmission lines. But that would be an incomplete answer, because if you just connected transmission lines directly from there to you, there's two problems. One, there'd be huge power losses over the transmission line. Humongous. These are kilometers, hundreds of kilometers, even thousands and so on. And over that amount of distance, that amount of copper and aluminum and what have you, that's going to be a ton of power losses because of the resistances, the capacitances, and the inductances associated with the transmission line. So that's not possible. That's not reasonable to just connect the generation directly to you. It'd be too inefficient. Secondly, the generation usually occurs at 12 to 25 kilovolts. If you take 12 to 25 kilovolts out of your power outlet, you're going to die. You need 120 volts. That seems like a more reasonable number. So there's this voltage level difference, let's say. So how can we connect the two? How can we rectify the situation? First of all, we implement transformers. And as you can see in this basic system diagram of a power system, you have generation that occurs at 12 to 25 kilovolts. This is where some form of other energy is converted to electrical energy, usually some other energy into mechanical energy to drive turbines, which drive the generator, which creates electrical energy, and then a unit transformer right after. And this unit transformer is the first transformer encountered in this system. It takes that 12 to 25 kilovolts and bumps it up to 110 to 1 megavolt. And you'll see that this bumping up heavily reduces the power losses because now the current is down by the same amount of factor, and we know losses primarily are I squared R losses. Those go down by a square of that factor. So now we have a ton less losses. Then we have transmission lines. Usually those lines are, the following voltage levels. This is something you'll see if you take a power systems class, 138 kV, 230 kV, 345, and so on. And then coming down after a certain amount of distance, you have your substation. And this is where this is a lot closer to you in terms of distance. What it does is it brings that whatever high voltage power line back to the voltages seen originally at the generation, 12 to 35 kilovolts. So this essentially acts like bringing that generation plant a whole lot closer to you, making the distance seem much smaller than it would over there. So you brought all the benefits, all that power that you wanted from the generation, a whole lot closer to you without having to bring the entire power plant closer to you. Ain't that beautiful? Ain't that kind of really cool? So anyways, you have your substation transformer bringing that down. This is the second transformer encountered in this system diagram, and that goes through local transmission. And then eventually you see a distribution transformer, and this is what you might see if you ever looked up next to your house looked at the power lines. You'll see on those posts at the top, you'll usually see some kind of cylinder or maybe a square box. That would be your distribution transformer. That takes that 12 to 35 kilovolts and brings it back down to 120, which will go into your house, and that's what you see. And there you are, a happy customer, maybe even with your own Tesla. Amazing. So, you can see here we've encountered 3 transformers in this power system, each one crucial to the way the power system operates. And overall, this has made civilization possible as we see it today. If transformers did not exist, if we removed these 3 transformers, then guess what? That generation is going to have to be put right next to you. There'd be very little distance because any distance would create a ton of power losses, which cannot be afforded by either you or the generation company, the utility company that's producing that power. Okay, so this is the huge role that transformers play. Of course, we also know transformers are there in power electronics. You see that a lot as well, but I'll stick with this. This is the main point of transformers as far as we're concerned. Well, let's imagine this scenario. Let's say you have a generator supplying power to a load, and then you connect them with a transmission line, and let's ignore the transformers for a second. Then, okay, the generator is supplying a certain amount of power. Some of that power is going to get lost in the transmission line, and your load is going to get whatever's left over. And let's say your load requires a certain amount of power. Well, guess what? Your generator has to generate more power than the load needs because it has to compensate for the transmission line. Also, let's talk about operating voltage. Your load is going to need to operate at a certain voltage level. Because the transmission line is there, kind of just basic voltage division, the power generation needs to occur at a higher voltage in order to, get that required voltage specification at the load side. And so we have a problem. Okay, this transmission line is kind of taking away from the load some power, and it also is pushing those requirements not to the customer. Obviously, you're not going to change your requirements. The utility company is going to have to produce more power and operate at a higher voltage. Now let's say you put your transformers in between. Let's say you put a 1 to 10 step up transformer and a 10 to 1 step down transformer. We'll observe that the turns ratio here is 10, or 1/10, sorry, and the turns ratio over here is 10. Well, going from class, you should know that the impedances from the perspective of the generator, you can kind of translate those over across the transformer, and what you end up getting is your generator. Your load stays the same. If you translate it there, you multiply it by 10 squared, and then you multiply it by 1/10 squared, so that's the load. It's going to be the same as is, but your transmission line, that's going to get translated over and is going to get multiplied by 1/10 squared. And so there's what you have it. And so look, now instead of your transmission line direct connection and your transmission line impedance appearing between the generator and the load, you get the same load, same generator, but now the transmission line has gone down by a factor of 100. Its impedance has gone down by a ton, which is amazing. Now the overall kind of, let's say, output impedance is a whole lot less of your generator plus transmission line system. And so your load sees your generator doesn't need to work at a higher voltage. It can operate at a much lower voltage level, much closer to what the load spec is, and it doesn't have to put out as much power because the transmission line power has been reduced by that factor of 10 squared as well. And so that solves both problems, and that's the big, kind of basic idea from class of what transformers do in this kind of power distribution scheme. Let me show you guys a quick demo. This is not part of the lab, but I want to show kind of a scenario of where you have a generator far away from a load, and we're connecting the two with a transmission line, and to compare that with what happens when we connect transformers in and see and compare the two situations. So what I have set up here, like a maniac, you will see in a second, I'm going to run this synchronous generator. I'm going to run it as a generator. It's going to be driven by this prime mover, so it's just a DC motor here. It's going to drive the generator, so the generator is going to rotate and it's going to produce some power. And I'm going to take the generator's power and I'm going to supply power all the way to a load over there on the chair. It's kind of hiding behind the chair, you can see. And I'm going to connect the two just directly with this transmission line. Okay, let's call this a transmission line. I basically used up all the blue wires from class to produce this because I wanted as much impedance in the transmission line as possible, because these are still, this is still not even close to scale. Transmission lines are, hundreds and thousands of kilometers long, and put down to scale, it would still be more than what you're seeing here. But let's see what happens. So I have the load connected here on the load side, and then the ground wire going back to the generator. And I have displays over here showing the power between the two, on how much, so that I can see how much power the load is receiving and how much power is being generated over there at the generator. Okay, so let's go ahead and compare the two. So I'm going to go ahead and start the generator here. By the way, you guys are going to do this for lab 4, so sometime in the future you'll see the next lab is on induction motors and the one right after that is on generators. So get excited, get hyped. But anyways, I'm just going to go ahead and start this up. This may be loud, so I hope I can speak over it. All right, I've worked my way up over here. So the generator is running. All I'm trying to do is run the prime mover enough so that the generator is outputting 1 amp. And indeed, that's what the case is. So the phase that I'm taking out of the synchronous generator it's producing 48 volts, 1 amp. So the amount of power output is 49 watts. I'll note that this is very inefficient the way I'm doing this, because I'm putting in 113 watts, I'm getting out 50. This is less than 50% efficient the way I've set it up here, because I'm just using one of the 3 phases of the generator, and you know, this conversion between the dynamometer and the generator, kinda you could say. We'll see that in the future lab. But anyways, 49.4 watts, let's say 49.5 watts on this side. Let's go over to the load side and see what it's seeing. You can see here, there's the load, and what I see is 49 watts. So not much of a drop, you know. Let's say this is half a watt drop from what it was over there, but you can see the voltage is a little less. It's 47 rather than the 49 we were seeing, and obviously everything is in series, so the current is the same. But you can see the load is getting less voltage and less power than what it wanted, what we set it at over there. And those losses are because of this long transmission line. Now let's see what happens when we put a transformer. Okay, so now I have the transformer set up. I basically connected between the generator and the transmission line. I set up this transformer. This is the primary side, is the way I'm setting it up. It's a 120 to 208, so basically almost a 1 to 2 step up transformer on this side. And then on the other side, on the load side, I have just the opposite. I'm going from 208 to 120, so almost 2 to 1 step down transformer, and then everything else is the same. So let's go ahead and start this up. Now ideally, because I'm stepping up by 2 and then stepping down by 2 on the other side, approximately, I should see those losses go down by a factor of 4. We were seeing maybe a half a watt loss before. Now we should see something like a tenth of a loss, maybe even they're almost exactly pretty much the same power from the generator side to the load side. So let's go ahead and test this out. I'm going to do the same thing. I'm going to crank up the dynamometer, the prime mover, until I'm outputting 1 amp from the generator. So let's go ahead and do that. I'm going to go ahead and start this up. Alright, I'm about 1 amp, and you're gonna see a problem right away. 1 amp, but look at my voltage. Instead of 49, it's 56, so it's higher, which is not good. We wanted to see lower. And look at the power, it's like 59 watts. But okay, let's compare this to what it was, to what is at the load side. So 59.3 watts, let's say, from here. Let's go over to the load side. Great, the computer decided it wants to sleep right in the middle of a demo. Let me log back in here real quick. But yeah, as we can see, we see that 1 amp, but look, 48 watts. It was 59 over there, 48 over here. What the heck happened? Why did the addition of the transformers do the opposite of what I've been talking about for the past however many minutes? What's the problem? Let me turn this off. And the problem is transformers are not ideal. Okay? We've been talking about them as if they were these ideal, beautiful devices that just worked with no issues. But no, as you'll see in the lab today, they are not ideal. They come with their own issues. And in this particular scenario, instead of solving the problem, and it wasn't much of a problem, they ended up adding problems that weren't there to begin with. And we're going to study that in the lab today. So let's go over some more background material. Okay, so in what ways is a transformer not ideal? Well, let's talk about that. In class, you guys learned about the practical transformer model. We've been thinking about so far this ideal one. And in the ideal case, we have zero resistance in the windings, perfect flux linkage between the two windings, no core losses at all, no magnetizing losses. That's wow. And in terms of translating the practical transformer model to this ideal one, I've written down some stuff. But let's go over the practical transformer model for a second. So in the practical transformer model, of course, any transformer out there, any of those windings, they're going to have some resistance. So we have some primary side resistance up there, that RP, and some secondary side resistance, that RS over there. On top of, and that's the obvious one that most people would think of. What about these other ones, this XP, XS, and this shunt resistance and the shunt reactance over there? What are those about? And actually, that's something that is not really properly taught in class. You guys are just kind of given what XP is, XS is, RC, and so on. You guys just learn about the open circuit test, the short circuit test, and that's it. You don't put those actual impedances into context. Now the book, which of course nobody reads, but the book it goes over a explanation, a theoretical explanation as to what these represent really, and it's great. You should go over it. I'm not going to go over it because it's a lot, but I'm going to give this the summary, the overview. As we said, the resistances represent the winding resistances. They are the most obvious thing. The series reactances, they represent what is called flux leakage. Okay, we have windings on one side, windings on the other side. We want the magnetic fields, that magnetic flux, as much as possible on the primary side to go onto the secondary. But some of that magnetic flux is not going to go through the secondary. It's going to go, away from it. It's going to go outside. It's going to miss the secondary by a little bit. So that's what we want. The magnetic flux going through the primary, we want as much of that going through the secondary. The difference in the two is accounted for with that series reactance over there. And we see the same thing for the secondary as well. And then, okay, what's this RC? That is the kind of, in a way, the resistance of the core. Because we know the core itself is conductive. When you have changing magnetic fields, the way this transformer works is we have changing magnetic fields on the primary side. They induce they produce, they overall amount to a changing flux in the secondary, which by Faraday's law produces an electric field, which will produce an induced EMF, and we get current. Okay, but also that happens in the core itself because the core is conductive. It's not made of plastic or something. It's made of iron, which is a metal. So it will also have this action upon it. It will also have Faraday's law act on it. And so we get also induced currents, induced EMF in the core, and so induced currents, those circular currents. And as a result of that, we have some losses in the core, and that's what that RC is, because some of that power on the primary, it's not going straight to the secondary. Some of it's also put into the core, which is pointless. We don't want any current in the core. We're not using the core for any current, but there is going to be some. That's what that RC is for. Okay, and we also have this XM, this shunt reactance. That represents magnetizing losses. That represents the effects of what hysteresis would produce. Hysteresis is when you kind of have to go through a different curve along the hysteresis curve, as in to demagnetize. Actually, this would be a better explanation. To demagnetize the core and produce the other direction, because okay, when you're magnetizing and then you're demagnetizing and then you're magnetizing in the opposite direction, right? That's what this changing magnetic flux is trying to do to the core. You're trying to have the core, its overall magnetic moment switch, dipole moment switch back and forth. This switching cannot occur perfectly. There's going to be some lag. Some energy is going to need to be spent to switch those magnetic moments, those magnetic dipoles. And so that amounts to hysteresis losses. And it also is a basic way of describing how much current you need in order to magnetize the core. If this JXM, if this reactance is really small, that means it has a very high admittance. That means you need a lot of current to magnetize the core. Ideally, it would be infinite, in which case you need barely any current and your core is immediately magnetized. Okay, so that's what these parameters are for. Series winding losses, the RP and RS, flux leakage losses, those XP and XS, the core losses, the RC value, and magnetizing losses, that XM. Like I said, go to the book. It will give you a more in-depth explanation to this kind of stuff, or just email me and ask me questions. But like I said, translating this into the ideal transformer model, in the ideal model, we have zero resistance, so no winding losses at all. We have perfect flux linkage. All the magnetic field, magnetic flux going through the primary is perfectly into the secondary, and nothing's coming anywhere else. So almost like a confined magnetic field, which is of course impossible. We have no core losses, which means that core, even though it's conductive, somehow it's not getting any induced current into it. And so it's a perfect core, no losses at all. And then magnetizing losses are none. And we see the corresponding values. If it was ideal, we want RP and the series resistance, series reactance, we want those to be zero. And the opposite for those shunt impedances, we want the core resistance to be infinite, and we want that magnetizing reactance to be infinite. So we want those to be really high, these to be really low. Okay, so that's the practical transformer model. So I'm going to take that and let's try and build a transformer. We're going to go through some steps, and I think that will provide a lot of insight. Okay, so let's build a transformer. What do I mean? Well, we can start with step one. Technically, you could have a transformer if you just had one loop of wire on one side and the other loop of wire, next to it somewhere in space, and you somehow ran alternating current on that first loop. You will indeed get some transformer action, and you will see, due to Faraday's law, you will get on the second loop, you will also get induced current. It's not going to be very much, but it's going to be there is going to be some over there. Now, how would we characterize these two loops in mid-air? How would we characterize that with the practical transformer model? I know that seems weird, but this will be insightful actually. So let's talk about it. Let's talk about those series impedances. The series resistance, that's going to be really low, right? We just have one loop of wire and that's it. So the RP and RS values, the primary and secondary resistances, they're very small, which is good. That's actually something that we want. That's close to the ideal model. What else do we know? The RC value, that core resistance, well, what's the core here? It's air. That's barely conductive at all. So its resistance is pretty darn high, which is also a good thing. That means that there isn't going to be much eddy current, of course, in the air, and so very little eddy current losses. As a result, those are actually two happy faces. Those are good things. In the style of Dr. Green, I drew the smiley faces over here. But anyways, but there are obviously two negatives. We don't have transformers like that because of two major problems. One, the flux linkage is incredibly poor. There's barely any flux linkage. The flux going through the primary, most of it's actually just looping around. If you took physics and you remember how the magnetic field around the loop looks, you're going to see most of that flux is just going right around the wire, and that's it. And it takes very few magnetic field lines, let's say, in a way, very few magnetic field lines actually reach the secondary. And so we have very little changing magnetic flux on the secondary side compared to the primary, so the flux linkage is really poor, and so we have that X value, that series reactance, is really high, which is very poor. That's a big sad face. Okay, that's going to be very problematic. Also, the amount of current you have to run to magnetize that space in between is going to be huge, and so that XM value is really small. That shunt value there is going to be really small. It means you need a lot of current to magnetize that space in between, which is again no good. We want very little current, and we want to magnetize the core immediately. So that's obviously a non-ideal core. That's just air. Air has a magnetic constant of pretty much 1. So that's no good either. That's no bueno. So we have some positives, but we have some big negatives. So let's improve on this. Let's start by putting a core in between them. Let's keep those loops and let's keep those two loops. But now let's insert an iron core in between, something that has a very high magnetic constant. Well, okay, what changed now? The resistance of the windings is still pretty low. We still have those one loops. Great, that's a big plus. However, let's see what else changed. We see that the core resistance, before the core was just air, so its resistance was really high, which was good. Now there's an iron core. Now the resistance is lower. It's not as high as it was before, so that RC value kind of went down, which is not good. We want it to be infinite. So now we are introducing indeed some core losses. There are going to be some induced eddy currents, which will be circles around those magnetic field lines, similar to how an electric field would be induced with a changing magnetic field through a surface. But anyways, we're going to see some eddy currents in the core. And so that's gone down. That's no bueno. Now the happy face turned kind of into a plain face. But as a result, something that improved, those two big negatives became slightly less negative. We see some better flux linkage. Now the magnetic field really is a lot stronger in terms of how much is connected between the two. The flux change in the primary is a lot closer to the flux change in the secondary, so that's good. There's better flux linkage now. And also, we don't need as much current to magnetize the space in between them as we did before, so that shunt reactance value has gone down. It's gone up from what it was before. It was 3 big down arrows. Now it's a 1.5 down arrow. So okay, we have improved the design a little bit by inserting a core, but we want as much happy faces as possible. Let's see how we can add to this to get the transformer even better. Okay, so we put a core between our single loops, and that improved things like the flux linkage, but we still had, we still had kind of red flux linkage. We still had a sad face for the magnetizing reactance. And the core losses were, I mean, okay. But okay, let's try and improve on that. Okay, let's, instead of having just one loop in here, let's actually have multiple windings on both sides. Now what happens? Well, a couple things have improved, but we see some things kind of also went down. It's not perfect. It's not a perfect situation. So for one thing, now the flux linkage is really good. Now we have green happy faces for that, because now, because of those windings, we know that the magnetic field is proportional to the number of windings. Now we have increased the magnetic field, which, and also the same rate of change. So we've also increased the magnitude of the rate of change of the magnetic flux. So higher induced voltage on the other side, and also overall better flux linkage. Because the magnetic field, let's say, stretches out more because of the increased number of windings. So increasing the number of windings, that's like this third step over here of our progression, that improved the flux linkage. Great. It also improved our magnetizing reactance, because now we don't need anywhere near as much current to magnetize that core, that space in between them, because of the number of loops. Like I said, the number of loops increases the magnetic field in a proportional manner. So now we can use, with that same factor, a lot less current to produce the same amount of magnetic field in the core. Great, so now our reactance has gone a whole lot up. So now we have two happy faces. We've decreased our series reactance and we've increased our magnetizing reactance. Bueno. However, we're using more windings now. And that is a problem, because now our series resistance, before it was just one loop of resistance, which was nothing, now we have some resistance, and the number of turns here could be 100 or 1,000, in which case you're using a decent amount of copper, and that does cause some issues. So our resistance before, while it was a big happy face, now it's kind of neutral. Now it's kind of a, I'm not really sure what to make of that. So it's not great, but it's not terrible yet. So we're not just like a total deep end. We're not a red sad face, but we're kind of less than what we were before on that front. And we'll also realize that with stronger magnetic fields, now we have more core losses. And indeed, we have a sad face for that now, not just a neutral face like we had for step number 2. Because the stronger magnetic fields are going through that core, and we're having stronger polarizations and all that, we are indeed having stronger eddy currents, which means more core losses. And if we just left this as is and we didn't do anything to the core, this would pose a major problem, because those eddy currents could be high enough that it would actually heat up the core. And when you heat up a core, this magnetic capability is drastically reduced. That magnetic constant that we are craving so much in a good core, that goes down. That will definitely change. And we also get more non-linearities in the core. And so keeping the core as is and having a transformer just like that, that's not going to be effective. That's not going to work for a practical transformer. But anyway, so we see now 3 happy faces overall, 1 sad face. Can we turn that sad face at least into a medium face, so we have all green and we're good to go on a practical transformer design? Indeed, yes. What an actual practical core is not just a solid block, but it's layers of sheets of metal, of that iron, stacked on top of each other and insulated from each other. And so you kind of have layers of insulated metal stacked on top of each other, so there's a whole lot less volume for that current to run through. Before it was one solid block of volume, now it's a whole lot, little layers that the current can go through, and that's it. And that makes for a lot more resistance. And so if you laminate your core, you increase its resistance, which decreases these eddy current losses. And so now we have what we see on the bottom there, at least all green. We kind of have, the resistance of the windings has not changed. It's still the same number of windings, but it's still kind of the flux linkage is still the same, which is something good to note. By adding the laminations, by making the solid block into sheets, we don't drastically change the constant at all. It's pretty much the same, the magnetic constant of the material. So the magnetization is still good, and that same applies for the magnetizing reactance. And so now we have all green, and depending on in this particular design, this is what a lot of practical transformers are like. And indeed, that's what you learned in class. You saw that kind of squarish. This is what is called a core form transformer. And on one side, windings on one side, windings on the other side. This is indeed a practical transformer that is designed and built today. Although it's not the most common. Okay, and we're going to get to that. We're going to look at the transformer we have in the lab right now. Okay, so we kind of qualitatively talked about how a good transformer's parameters should be, right? Low series resistance, a really good flux linkage, a high resistance core to minimize eddy currents, and also a high shunt reactance in terms of how the core deals with hysteresis losses and all that. Okay, so we kind of discussed those parameters. Now, the question comes to how can we, so we just qualitatively describe them, but what is a good value? What is a good value for all these parameters here? What's a good value for our equivalent, our X primary, our RC, and so on? What are good values for those? And also, how can we compare transformers? So if I wanted to compare the performance of this transformer to the performance of these ones, these are rated for different voltages and different currents. Can I still compare them? Can I say this one is equally as good as that, even though they may have different parameters? Indeed, we can. And that's the beauty of the per unit system. And I'm going to go over that in a second now. So you guys learned this in class. You learned about the per unit system in terms of how useful it is in analysis of let's say a power system, especially one involving multiple transformers. It makes it a whole lot easier if you converted everything to per unit and then just analyze the circuit, the system one go, without having to refer impedances back and forth across a transformer. Even though that is also a very useful way of going about, an intuitive way as well of going about analysis of such systems. But anyways, in class, you learned about the per unit system and its usefulness for analysis, but also it's very useful to characterize all these electric machines and magnetic devices that we're working with, including transformers. If you can describe the transformer impedances, these parameters, in terms of per unit, then we have a very nice range of values that we can say for per unit are good. Characterize a good transformer. So for example, if you converted, first of all, if you referred all the impedances to one side so that you have an R equivalent and an X equivalent, here I referred it to the primary side. Remember, if you're referring anything from secondary to primary, you're multiplying by the turns ratio. So that R equivalent there, I wrote down, it's the primary resistance plus the secondary resistance multiplied by the turns ratio squared. And I also put approximately because you're referring, but there are the parallel branches there, so we're kind of referring across those as well. But anyways, approximately that's the case. In any case, just remember how to refer impedances back and forth. Refer everything to one side, and then if you converted those values to per unit, you'll find that if they fall in these ranges over here, you have a good transformer. If your R equivalent is 0.01 per unit and so on, going down the list, then you have yourself a good transformer. If you forgot how to do per unit, here's a real quick rundown. Just note down your base for your power and the base for the power of the transformer, the base rating for the voltage on the primary side, voltage base for the secondary side, and you can just use the transformer's rating. So for example, if you had a 1 kVA transformer, use that for your S base. On the primary, let's say it's 1 kilovolt to 2 kilovolts, so use 1 kilovolt for your base unit for your primary, 2 kilovolts for your secondary voltage base. Once you have those, then you can just go ahead and derive all the other base quantities. For you just want the impedance base quantities, and so Z base on the primary is equal to the V base on the primary squared divided by S base, and so on. And then you get, once you have your base unit for your impedance, you can get the per unit values for all these by just dividing the actual values by your base unit, and then you get the per unit values. And then again, if they fall within those, then you have yourself a good transformer. And this is actually an incredibly powerful idea, because you can compare a transformer that works in your microwave to a transformer that operates, to that unit transformer that operates from the generator and turns to that 30 kilovolts to 100k kilovolts plus and so on. You can compare both transformers just as easy, no problem, using this per unit system, because both their performance you can characterize using those parameters over there in per unit. So it's a wonderful thing. Per unit is very useful, and we're going to use it in today's lab to characterize the performance of our transformers. Okay guys, now to go over one last concept. I know I talked a lot for this lab. This seems like an overwhelming amount of background material, but like I said, this is one lab, so we're kind of having to cram in a lot of concepts in one, but I want to make sure everybody understands as much as possible about transformers. Last part voltage regulation and efficiency. This is another way to characterize the performance of your transformer. We discussed that, we have the per unit system. If we converted all our impedances to per unit, we can characterize our transformer. Another important thing to characterize it is voltage regulation and efficiency. And this is something of huge concern to an engineer. So let's talk about them both. Voltage regulation is this idea. So let's say I just drew out the transformer there, and I just drew that series resistance, a series reactance there. And actually, usually that's the dominating one in a transformer's parameters, and a lot of analysis is done by just assuming that the resistance and the shunt, those parallel branches, are negligible, and we can just take that series inductance over there. But anyways, let's say we have a transformer here, and we're applying a constant voltage on the primary side. Okay, it's not changing. We're keeping VP there as is. Now let's look at the secondary, and we want to know how the secondary voltage changes with the amount of current draw. If we're drawing a ton of current versus no current at all, does the voltage on the secondary remain the same? Does it go up or does it go down? And what you'll find, and what you should see in the book, and I think you should have examples in class for this, but you'll find that the voltage on the secondary will indeed change, of course, because anything that is a power source has some output impedance, and so it is gonna be affected, that voltage that the load sees, depending on how much current it's drawing. And so we'll find that the voltage on the secondary changes with respect to the magnitude of the current being drawn, and also the power factor of that current. So if you have an inductive load versus a resistive load, both will see different changes in that secondary voltage that they will actually get. Okay, and voltage regulation is what quantifies that, and that quantity VR, the equation for it is there. The no load voltage on the secondary minus its full load voltage divided by its full load voltage, and then in percentage. And you can see here, if that full load voltage is lower than the no load voltage, that means that Vs goes down as you draw more current at full load. Then the voltage regulation is positive. And so if you have a positive voltage regulation, then in a way your transformer will go down and its secondary voltage will go down if you draw current from it, which we kind of expect. That kind of makes sense. That's what we see out of most power sources. However, it is also possible for the voltage regulation to be negative, as in that the secondary voltage is higher as you draw more current from it at full load versus no load, which is a weird concept to think about. That's kind of counterintuitive. That's not what we see with other kinds of power sources. But that's why I say that power factor comes into play. And you'll find that the power factor affects the effect of power factor can indeed make you see that the secondary voltage is higher at full load than at no load, which is weird, but it works, and the book does go over examples for this, and you look at vector diagrams to show this more intuitively. I'm not going over that. We'll just experimentally see how this works. But voltage regulation, very important to characterize a transformer. We also have a good range for this. Usually plus minus 10% is the range we want to stay in for our transformer. If we're outside that, then the voltage regulation is bad. Okay, so we usually want to stay plus minus 10%. Finally, efficiency. We all know efficiency. It's power out over power in. And then I just wrote this out a little more. Power out is that input power, but subtracted from it some losses, right? Because we have losses in our transformer. We saw that very clearly in the demonstration. We had a whole lot more losses than what we kind of improved on reducing the transmission line losses. And then those losses can be primarily split into can be just split into the copper losses in that series winding, in the winding itself, the copper losses in that, plus the windings, plus the losses in the core, which includes hysteresis, but mainly eddy current losses, okay? And so that's what we have there. And I just wrote out that the copper losses are the magnitude of the current squared, I squared R losses. I'll be careful with that. R equivalent is referred to one particular side. So if you're looking at the primary side, R equivalent, then that I squared is that primary side current. If everything was referred to the secondary, then you do the secondary side current squared times R equivalent on the secondary. But anyways, using these, you can characterize a bunch of things, and we're going to see that in the lab today as well. And this is important in characterizing your transformer, okay? All right, finally to the actual, experimental procedural kind of stuff. We've talked about the parameters of the transformer a lot. how are we actually going to obtain those parameters to begin with? Let's say you found a transformer out, in the street somehow, or you're just trying to test a transformer to get these parameters that we've been talking about. How would you go about doing that? We have two tests. We have the open circuit test and the short circuit test. I'm going to note, and this is something I observed experimentally last semester when I did this, made this lab manual, that the open circuit test has important limitations, and I'll mention that, but the short circuit test not so much. Okay. In any case, the open circuit tests allows you to gain those parallel branches, those shunt parameters, and the short circuit test gives you those series parameters. And the general idea, the general way you go about it, is designate your transformer, designate a side as primary and the other side as secondary. It doesn't matter which is which, just be consistent. Choose one side and stick with it. Okay, choose one side as your primary and the other side as your secondary. All right, and we'll start with the open circuit test. So what you're going to do is basically you're going to choose one side to apply voltage to, and the other side you're going to leave open circuited. Okay? And when you apply voltage on that side, with the other side being open circuited, effectively you're negating the result of those series parameters. That's why when you draw up your model for your open circuit test, you just ignore the series impedances. Because of the fact that the other side is open circuited, in an ideal transformer, by the way, if the other side was open circuited, then your primary side's impedance, the impedance seen by your transformer, is going to be infinite, and you're not going to get any current when you apply voltage to that primary side, or in this particular case. Okay, but because there is current that will come, that current is due to the shunt admittances here, which is what you're going to calculate. Okay, but anyways, you're going to choose a side. Now there is a sensible side to choose. Usually transformers have a high voltage side and a low voltage side. Now whichever one you happen to pick as your primary or secondary doesn't matter, but both sides will give you the same result, whether you choose the high voltage or the low voltage side. So it makes sense, just to be more safe and to be more practical to work with, we're going to choose the low voltage side to apply voltage to, and we're going to leave the high voltage side open circuited. Now for this lab, it doesn't really matter because these transformers, they're pretty, either side is fine. We're not going to go crazy with the voltage. But if you're working with a really high voltage transformer, then it might matter. If you happen to take out a microwave transformer and you wanted to test it out, one side is going to be kilovolts. It's going to be, 2 or whatever, 1 kilovolt plus. And the other side is going to be the 120 that comes from your wall outlet. So obviously, the one that you would rather apply the open circuit test to will be that low voltage side, because it's a lot easier to get 120 than 2 kilovolts, and so on. And you will see, if you work with transformers, I think you'll come across that more and more. In any case, choose whatever side, choose one side, and the low voltage side is the more sensible choice. Once you choose that side, as a huge thing to help prevent you from making mistakes, because there are some mistakes that can come up with these two tests, draw your schematic right away for this test. If you chose the primary side, that's the example I drew out there, draw that circuit, okay? The reason why it's important to designate and be consistent about which side you're on is because at the end, you want to combine all your impedances to one side and then do the per unit, let's say, conversion, and then we can tell the transformer's specs if they're, good or not. In that referring everything to one side, we need to remember which side we're referring to. So for example, for this open circuit test, if you're doing the primary side, then those shunt admittances, those shunt branches, they are referred to the primary. We can refer those branches to the secondary later on, but we have to remember whatever values we're measuring right now, whatever we're calculating experimentally, those are referred to the side you chose. And here we chose, in this example, I'm choosing the primary. So those are the primary values of those shunt branches. Okay? After you've drawn your schematic, just to help you prevent making mistakes and to remind you that this is primary side, go ahead and apply some voltage on that primary side. You're going to see some resulting current. That's called magnetizing current, by the way. But anyways, I'm designating that as IOC. And VOC times IOC, the real part of that will be the power. That's real power, POC. Okay? And then with those values, which you just display on your multimeter window in the software, in the DAIM software, not DAIM, like DAIM software. In any case, you can obtain and calculate your parameters and have the equations over there. And that's just basic circuit analysis. It just makes sense. Okay? And so there you go. You have your values. I was going to say that the open circuit test has its limitations. This is where it has its limitations, okay? The values you calculate here are just for that voltage that you're applying. If you half that voltage, now ideally, it would result in the same RC and XM. Indeed, if you had the given RC value and the given XM value over there, regardless of the voltage that you put in, they are going to stay the same. They're not going to change with voltage. That's what you have with linear devices. But indeed, that is not the case. If you work with it, if you apply a different voltage than you did the test at, you're going to find your RC and XM values are actually different, which is terrible. That's not good at all. These values should be constant, or at least that's what this test is trying to tell you. And indeed, the book and in class, they make you think that these values are constant regardless of that voltage you apply, but it's not. So you apply the rated voltage for this test and operate your transformer at its rated conditions, because otherwise the parameters you calculate no longer apply and you may have something totally different than what you calculated, and you may find performance widely differing. So just be careful of that. The parameters here that you calculate, they're purely for that voltage level, and that's because of that you should apply rated voltage, because that's what your transformer should be working in. Now that we're done with the open circuit test, the short circuit test is just kind of the opposite. So again, we choose a side to apply, and this time we're going to apply current to one side and short the other side. Now, because we're applying current to one side, we want to choose the side that has less current, okay, that we need to apply to. And so again, a sensible choice is to choose the high voltage side, because the high voltage side of a transformer is the one that will have lower current rated. And so we choose the high voltage side. And if you chose the low voltage side for the open circuit test, the other side is the high voltage side. That's where you apply your short circuit test. And the way you do it is, like I said, you're going to apply current to that side. The other side is short circuited. Once you've chosen your side, draw the schematic again to make sure you're not making mistakes. And this is where it comes important, because we chose a different side than when we chose for the open circuit test. Those values are referred to the primary. For the short circuit test, if you chose the other side, they are referred to the secondary. So just be careful of that. Be very mindful of the sides that you're choosing here. And remember, you're going to refer all the impedances in the end to one side. Okay? Anyways, once you've drawn the schematic, go ahead and apply the current. A big warning here, when you're applying the current, because we're using a voltage source for the current, we're not using a current source, don't apply rated voltage. Okay? If you do that, goodbye transformer. You just blew it up, because the other side is shorted. If you apply full voltage there, then that other side is going to receive whatever the voltage turns ratio is, but it's going to see zero impedance. It's a short there. So be very careful. Do not apply rated voltage for this test. You want to apply rated current. So you're going to raise the voltage very slowly, and you're going to find the current rising really quickly because the other side is short circuited. And so raise the voltage slowly until you see the rated current, and then you're good to go. A note, the rated current is not immediately apparent on the transformer on the module itself, and it's also usually not directly apparent on the nameplates of transformers you might see outside. And that's because you should be able to, on your own, calculate what the rated current is. You know the power rating, you know the voltage rating on the secondary or the primary or whatever it is. You can calculate what the rated current is easily. So that should be something you can calculate on your own. Anyways, once you've hit rated current, go ahead and measure these values, the power, short circuit power, and the short circuit current, and then you can run through these calculations and obtain your parameters. This is again just basic circuit analysis to obtain these values. So all right, there you go. Now you've performed your tests and you have all your parameters. Once you do that, combine everything on one side. Okay, either everything to the primary or everything to the secondary. It doesn't matter. Just combine everything. This is where, again, it's important to remember which side you did the tests on. Once you combine everything to one side, go ahead and convert everything into per unit. And now once that is done, you can characterize your transformer as a good one or a bad one based on the ranges we discussed previously. All right, and those are your tests. I'm going to go ahead and do the experiment now with these tests. Alrighty guys, here's the experimental setup. Now you're going to be surprised that the really long background that I went over will end in this relatively short experiment. Okay, so I'm sorry it took a whole lot, but the background was important to make sure that everybody understood. So here's the experiment. I'm just setting up the open circuit test. So what you guys are going to do is you're going to take my measured values and you're going to go ahead and calculate the parameters for me. So this first part of the lab, part A, is we're going to characterize the single phase transformer. And specifically, we're going to characterize it when we're using the 120 volt as the low voltage side and the 208 volts, so terminals 3 and 4 as the high voltage side. And we're also going to characterize any one of these single phase transformers that constitute this 3-phase transformer. Okay, we're going to characterize both, and then we're going to compare them, and we're going to say which one has better parameters and what those parameters physically mean between these transformers. Okay, so that's part A for the lab. Part B will be voltage regulation and efficiency. Okay, but anyway, so I have this first step is to set up the open circuit test, and what I have is I'm going to choose for my open circuit test the low voltage side of this single phase transformer, where I have it between 1 to 2, which is the 120 volt side, and the high voltage side, the other side, the secondary, will be between 3 and 4, and it's 208 volt rated. Okay, so this is a 120 to 208. The turns ratio will be whatever. It's something like that would be √3 actually. But anyways, so that's my chosen side. So just note that. Remember my steps for the open circuit test. So this is my chosen side. I'm just gonna go ahead and apply rated voltage, and I'm gonna measure the corresponding current and the power as well. And I'll have my VOC, IOC, POC as a result. And then you can go ahead and calculate the shunt impedances accordingly. And remember that this is referred to the 120 volt side. I'm just going to call that my primary side. Okay, so I'll go ahead and apply. So actually, I'm not going to go directly to rated current. I'm going to do 30%, 60%, and then 100% rated voltage. And then we're going to, each one will have its own IOC. And the reason why I'm having us do the 30%, 60%, and 100% rather than just rated voltage right away is I said that the open circuit test has its limitations in it, that the parameters you get are just for that voltage level. You're going to see that now, and or at least you should. So okay, right now I'm going to go ahead and go to 30%, and I have the mirror set up. And right now at 30%, this is my VOC, this is my IOC, so around 11 milliamps RMS peak, and that's my POC. Okay, so that's at 30%. I'm going to go ahead and raise this now to 60%. And here we have the corresponding values again. So just note those down. And now finally, we'll go to 100% rated voltage. And there we go. Now we have our other rated values. Note that this current now jumped by a whole lot more than it did before. Okay. And so did the power as well. So just note those down and calculate the corresponding shunt branch impedances. Okay. Once you have that, I'm going to pause this and I'm going to set up the short circuit test for this transformer. Okay, the short circuit test is now set up. So really easy. I just shorted I'm choosing now the high voltage side to apply the short circuit test for. And I'm shorting the low voltage side, the other side. So this is shorted together. Yep, so this is shorted. And now this is the high voltage side. I'm going to apply current to this side. And I'm going to do that slowly until I get to rated current. And I'm going to note that this side is 208 volt rated. Its power rating is 60 volt amperes. So the current rating for this side, and actually here it's written, so this is fortunate. But anyways, the current rating here is 0.3 amps for this side, which amounts to just that 60 volt amperes divided by 208 volts. It'll come to 0.3 amps. So that's the rated current for this side. Here it's written down, but I didn't need to have this. This is just as easy as dividing this by whatever the voltage your side is on. Okay, and for example, we could have chosen other terminals. I just happened to choose the 120 to 208. If I wanted, I could have chosen this 60 volt side and this tap as my primary, and then I could have chosen 208 as my secondary, and then we'd have a different current rating for this here. But all of that is based on the power rating of the transformer. Okay, anyways, I have everything set up. I'm just going to slowly raise the voltage until I hit rated current, which is at 0.3 amps. So I'm going to go ahead and raise the voltage very slowly until I hit that 0.3 amps. So you see it came very quickly. I'm going to go a little under because I'm a little overrated. Okay, So go ahead and note those down. Those are the short circuit test values. This is VSC, ISC, and PSC. Okay? And note that I'm not going to do a 30%, 60%, 100%. The short circuit test, you can it's going to give you parameter values that are pretty consistent no matter what the current is, which is the nice thing about the short circuit test that the open circuit test doesn't have. Okay? So it doesn't have those same fallings as the open circuit test. Okay, so just note those down. I'm gonna move on now, and so that's it. That's the transformers, the single phase transformers tests. We can go ahead and calculate these parameters, refer all those to one side, and convert those to per unit, and note those down. Okay, that's what this part of the lab is for. I'm gonna do now these tests on any one of these three phase transformers. I'll just do the same stuff. You're gonna note the same stuff down again, and then you're gonna compare the two. Okay, that's this part of the lab. Okay, so now I'm starting the open circuit test for this a single phase transformer as part of this three-phase transformer module. I'm just choosing this one arbitrarily. Again, 12208. I just want to keep the same voltage rating so that we're close to the single phase transformer's choice as well. So we're choosing again the low voltage side for this open circuit test, and I'm gonna again apply 30%, 60%, and 100% rated voltage and show you the corresponding current and power consumption, and then you're going to calculate the shunt parameters accordingly. So I'll go ahead and do that now. I'll go ahead and raise the 30%. So that's the current for that. Notice, by the way, the current's already a lot higher than what it was for the single phase transformer, which means probably the shunt admittances or the shunt impedances are higher. So that RC and that XM values, those values are probably lower than what they are for the single phase transformer. Okay, I'll go ahead and raise this now to 60. And then now rated. Okay, and there you go. So yeah, you can see definitely it's a whole lot more power consumption and a whole lot more current that's going to the shunt branch than was for the single phase transformer. And I want you to be able to not just interpret that and say that those values are lower. I also want you to tell me what that means physically. So remember that XM kind of represents the idea of how much current it takes to magnetize the core, and that RC value represents the core's resistance for those eddy current losses. I want you to talk about that, okay? Anyways, that's the open circuit test. I'm gonna go ahead and quickly switch out to the short circuit test. All right, short circuit test setup. I'm choosing the high voltage side for my short circuit test because that's the lower current. And the other side, this high voltage side is, or this low voltage side is shorted. And I'm gonna go ahead and apply the test. And I'm just gonna raise the voltage slowly until I hit rated current. I will note the rated current is different now. Here it was 0.3 amps for the high voltage side. Over here, and again, it's written, but anyways, it's 1.2 amps for this side. But we could easily get that 208 volt side. The power rating of any one of these transformers is 250 volt amperes. So 250 over 208 gives us the 1.2 amps. If I was on the 120 volt side, I would divide 250 by 120, and that give around a little over 2 amp current rating on that side. Okay. Anyways, I'm going to go ahead and raise this until I hit 1.2 amps, which should be pretty quick. So we're at already 0.9. Okay. All right, I'm a little over. I'm going to go down. Okay, let's keep it at that. All right, there you go. That's the short circuit test value for this, for the single phase transformer from the 3-phase set. Okay, just go ahead and note those down and compute out the series parameters. All right, and now that you have both transformers calculated out or tested on, you should be able to compare them and tell me which one is better, which one is worse, and why. Okay, and by the way, there should not be one single answer. Probably they both will have their pros and cons, okay, relative to each other. All right, now next up will be part 2 of the lab. All right, now for the second part of the lab, this is on the voltage. We're going to characterize voltage regulation and efficiency, and we're gonna do that just for the single phase transformer. And we're going to test the voltage regulation and efficiency at different power factors. So we're going to start with a lagging power factor, and then a power factor of 1, and then a leading one, and see how the voltage regulation and efficiency varies across those. So the way I have this set up is I'm gonna apply voltage to the low voltage side, the 120 volt side of my single phase transformer, and then I'm gonna supply a load with the other side, the high voltage side. Okay, essentially this circuit from the lab manual over here. Okay, wait, let me just turn to that. Essentially this circuit over here. Okay, and I note down a couple of things. Make sure that you are using the values for R equivalent and X equivalent that you got from the previous from part A. Okay, and refer to the primary side. Okay, refer to the 120 volt side where I'm choosing here is the primary. So refer to the 120 volt side, use R equivalent and the JX equivalent. Okay, and then you're gonna apply a load to this side, and you're gonna note especially this value over here, I2, and we're gonna note E2 and E1. These will give us voltage regulation. You're gonna use you're gonna use I1, for efficiency. Okay, and that's all I'm gonna tell you. You should be able to get everything from that over here. So I'm going to show you the values now. I'm going to apply 120 volts on this side, and we're going to start by noting what the no load voltage on the secondary is. So I'm going to go ahead and do that. So it's at 120, it's at full. So at 120 volts, this is the primary, this is the secondary voltage. Okay. You should also note that, observe that the current on the primary is that open circuit test current. So basically nothing, okay? But yeah, that's the voltage at the secondary under no load. Now I'm gonna go ahead and put a lagging power factor load, which is the 600 ohm resistor in series with the 300 ohm inductance, reactance, I should say. And once I go ahead and turn that, observe now, things have changed. Look at the secondary voltage. Okay, it's not that 207, it's a lot lower, which means positive voltage regulation because this full load voltage is different. And also use these to calculate your efficiency. This should be pretty obvious. This is output, this is input. And based on the current values that you're seeing here, you should be able to calculate exactly what the copper losses are and what the core losses are. Okay, and I want you to calculate that out. All right, so this is for the lagging power factor load. Now we're gonna use a purely a power factor of 1 load, and then I'm gonna transfer that to a leading power factor load, and we're gonna repeat these steps. Okay. All right, now I have the purely resistive load, so power factor of 1 load. Again, this is at no load. I'm gonna go ahead and turn the load on. And okay, there we go. Once again, by the way, we see that the secondary voltage has dropped once we drew current from it, even at the power factor of 1. Although it's a little less dropped than what it was for the inductive load, the lagging power factor load. But anyway, still a positive voltage regulation. Now I'm going to go ahead and set up the leading power factor load with the capacitive load, and we'll see the same, and we'll see what the results are. All right, the capacitive load is set up, this leading power factor load. Once again, this is no load. And now that's full load with the capacitive load. Okay, you can see, by the way, all of these had a positive voltage regulation because that secondary voltage dropped. But if you had a strong enough capacitive load, so a very small power factor towards the leading side, you're going to find that the 208 on the secondary actually would go up rather than down, weirdly enough. Okay, but anyways, the way I set it up, you can see here the comparisons. Remember, again, all of these, remember the efficiency values to calculate that, and along with using these current values to calculate what the copper losses are exactly, and can infer from that what the core losses are. All right. Okay, and that actually wraps up this lab. You're going to characterize what the efficiency and voltage regulation of this single phase transformer is at those loads. And you're going to tell me whether that's good or bad based on what I gave in the background information. Okay? All right. Thank you for going through this lab and the whole background. If you watched that entire part, kudos to you. Everything I mentioned in that video is also in the lab manual. So you can just go through that as well. All the best.